PTP, Parallelized Tracking and Prediction with Graph Neural Networks and Diversity Sampling. Our work contributes a parallelized 3D MOT and trajectory prediction pipeline that can eliminate compounding errors. It's commonly agreed that perception and prediction are both important components in the autonomous driving stack. To motivate our work, let's quickly review what's the standard perception and prediction pipeline. First, the sensor data is fed into the pipeline as inputs, which are often LiDAR point clouds or RGB frames, or the combination of them. Second, a 3D object detection module outputs detection results, often represented by 3D bounding boxes. Then, a 3D multi-object tracking module takes the bounding box results from the detection module and obtains object trajectories up to the current frame. Finally, future object trajectories can be predicted based on its history trajectories obtained from the tracking module. Although we have seen significant progress in each individual component, such as detection, tracking, and forecasting, the pipeline remains the same. So we're wondering if there is any potential improvement that can be made at the pipeline level. There are various ways of changing this perception and prediction pipeline. In this work, the key question we want to ask is the next step the best place to perform prediction? For example, can we do prediction somewhere in the middle of the pipeline? To motivate our pipeline design, let's review what's the common issue in the standard pipeline. Essentially, every component in the standard pipeline follows the sequential order. This means that the downstream module takes the outputs of the upstream module as inputs. For example, the inputs to the trajectory prediction module are the associated history trajectories from the tracking module. As a result, the limitation of this sequential pipeline is that errors from upstream module will be propagated to the downstream module, which can hurt the downstream performance in some cases. Here we show a toy example. On the left, we have predicted trajectories for two objects, red and blue, in dotted lines, given the ground truth path trajectories in solid lines. On the right, we can see that if our tracking module made a mistake in the data association, then the predicted trajectories can be seriously affected, and in this case, the identity of the prediction is switched. So, how do we deal with this problem? To alleviate the compounding error from upstream to downstream, we proposed a parallelized tracking and prediction framework, which we call PTP. Also, our method can jointly optimize the tracking and prediction modules to further improve performance. To illustrate the differences, let's take another look at the standard pipeline, especially about the tracking and prediction modules. We can see that both modules have a similar feature extraction component, which aims to encode object features from past information, such as objects' locations. In addition to feature extraction, there are also module-specific components, such as matching unit and trajectory decoder. Based on these observations, we first use a shared feature extraction module in PTP. Then, we approach the tracking and forecasting in parallel, only for their module-specific components, and the entire PTP is trained jointly with multiple nodes. Here we show some of the results, demonstrating that our method can jointly track and predict object trajectories. Okay, so we have talked about the high-level idea of our parallelized pipeline. Now let's take a deeper look about how we do it. First question, what are the advantages of PTP? Because tracking and prediction are in parallel, association error in tracking will not be explicitly propagated to the prediction module. Also, because the feature learning process is shared, the whole pipeline is also more efficient and can learn more discriminative features that improve both tracking and prediction. Here we show an overview of our pipeline, which contains 3 modules: shared feature learning, 3D multi-object tracking, and trajectory prediction. First, for shared feature learning, we use LSTM and multilinear perceptron to encode objects' motion features, given their path bounding box trajectories. Then we encode contextual features by modeling interaction between objects. This process is performed using graph neural networks, where each node in the graph represents a single object, and edge features between nodes are used to model object-object interactions. The second part of PDB framework is 3D multi-object tracking head. We use multilinear perceptron to regress the similarity score between every pair of objects. This step is to construct the affinity matrix for matching. During training, we supervise the affinity matrix by comparing it with the ground truth. During testing, the affinity matrix is fed into the Hungarian algorithm to obtain the matching results and construct trajectories. Besides tracking, our pipeline also performs trajectory prediction. We learn a conditional variational autoencoder to predict future trajectories based on the node feature, which encode past trajectories and interaction between objects. Also, we used a diversity sampling technique that maps node feature to a set of latent codes covering various modes of future trajectories. In this way, we can increase the diversity of trajectory samples in our outputs. Here we want to expand a little bit more about the diversity sampling technique we used. To understand why we need diversity sampling, let's take a look at the toy problem. Here we have some contextual features such as past trajectories and their predicted future trajectories corresponding to 3 different modes. The blue mode has most data, while the pink and purple modes have little data. If we learn a generative model using this imbalanced data, the latent space will mostly be occupied by the blue mode. To obtain trajectory samples from the learned generative model, the standard approach will independently and randomly sample latent codes. Because the blue mode has higher likelihood, samples will most likely cover the blue mode and may miss other modes. In order to cover all the modes, one would need a very large number of samples, leading to no sample efficiency. To address this no sample efficiency issue, we use a novel approach that can produce diverse samples from a pre-trained generative model. Specifically, we introduce a learnable diversity sampling function that maps past trajectory to latent codes, which are then decoded into trajectory samples. The key difference lies in that we use a diversity loss on the samples to optimize the DSF, which in turn moves the latent code to cover more modes in the latent space and increase the diversity of the trajectories. Okay, now let's confirm if our hypothesis is correct through ablation study. The key question we want to ask is that if our parallel pipeline and joint optimization are effective. To answer that question, we first evaluate the prediction performance of our pipeline without adding the parallel tracking module. Results are measured with standard trajectory prediction error matrix, ADE-FDE. The additional ASD and FSD metrics are used to measure diversity of the trajectory samples, which stand for average self-distance and fellow self-distance. Then, we add parallel tracking module in the PTP pipeline, we can observe a clear improvement in the prediction performance across different metrics. This shows that joint optimization with tracking is beneficial to prediction. Okay, we have shown that tracking is useful for prediction. What about the other way around? To test whether tracking can benefit from prediction, we first disable the prediction module and evaluate the tracking module alone. Then we add forecasting module back, and we can see that performance is improved in terms of the tracking metrics. This shows the effectiveness of our parallel pipeline where joint optimization benefits both tracking and prediction modules. For more details about this work, please scan our QR code, which will direct you to our paper. Thank you for watching.